Welcome everyone to geometry. We want to take a look today at section 26, which is about coordinate geometry. And coordinate geometry is just taking a look at the things we've already seen and placing it on a coordinate grid, the Cartesian coordinates. So there's nothing really particularly surprising or special about this. It just becomes a little bit more of a conversation on the things that we're familiar with, connecting things to algebra courses, that sort of a thing. So let's take a look at that section. All right. So coordinate geometry. The first thing is that we can essentially construct our axes however we like and wherever we like. We know that there's a line, and right, there are many lines, and we can construct a line and orientate it, or turn the page, or turn the line, or consider the line that is horizontal, allowing us to identify what we want to call the x-axis. And then similarly, we can construct the y-axis because we know that there is a line perpendicular to the horizontal axis. So we get our horizontal axis and our vertical axis. And we can even choose the point that we are using for the origin, 0, 0. And we can do this in part because for every line, right, we have a one-to-one correspondence with the real numbers. So we can choose that correspondence in such a way, or identify the point O, where you're identifying that with 0 on the horizontal numbers here, right? The horizontal line has a one-to-one correspondence with the real numbers. So identify O as as where 0 is. And then do the same thing for the vertical line, right? The perpendicular line. So now we have numbers along each line corresponding to the real numbers, and we can identify points along the line and out in space. So that works out to look something like, of course, if I can choose a point here, and I will call it P, let's say, and it has coordinates u comma v. So the x value is u, how far out we're coming along the x-axis. And one thing that we can do is we can identify the x value of P, or the x coordinate, and we can do that by P sub x, and that would be the point u comma 0. So we've come over u, right? This is how far we're reaching in the x direction. So that's that point. And we can do the same thing for the y coordinate. So we can do P sub y, and that would be 0 comma v. Excellent. So that's right, there's nothing surprising. And the origin, that's not a 0, that's an O, is the point 0 comma 0. All right. So the axes, as we are familiar with them, no surprise. We can call this line X, and we can call this line Y. Instead of L and M, we can use X and Y, and that's fine. All right, so then what we can do is we can start talking about distances between points. And when we have 2 points that are, let's say here and here, so they have the same y coordinate but different x coordinates, then the distance between them is just the change in the x values. So when we have the same y value and different x values, then the distance between those 2 points is simply the change in those x values. Similarly, if we have 2 points that are vertical of one another, that is, they have the same x coordinate, but maybe, but different y coordinates, then, actually, oh, circled the wrong thing here. They have the same x coordinate, they lie in the same left to right, but vertically it's changed. So again, that distance is just from here to here. So that vertical distance is the change in height. So just y minus v, absolute value. Excellent. So those distances are pretty straightforward, and really those are resulting, right? Both of these are resulting from the previous definition of segment length. Right, we already have a definition for the length of a line segment, yeah, and this is that definition, but because we've conveniently identified our one-to-one correspondence using this, we can use that particular one-to-one correspondence to give us the distance between 2 points. So again, that's actually what we're familiar with already. We're just utilizing the already given one-to-one correspondence on the x-axis and the y-axis. So then things get a little bit more interesting when we say, all right, well, what about points that are not horizontal or vertical of one another? So then we get the distance formula. And this we are familiar with as well. It's the usual distance formula. So distance from P to Q is given by the square root of the change in x values squared, so x minus u squared. So if you did larger minus smaller, smaller minus larger, doesn't matter. When you square it, it gets rid of that negative sign. And then plus the change in y values squared, y minus v, there we go, squared. And there we are. Now, if we have that there's no change here, this would simplify to what we have up here. And if there's no change here, this would simplify to what we have there. So that's very convenient. That's very nice. Square root of something squared is the absolute value of it. So we see that these definitions match, which is good. But this, we should also notice, this thing here is results. We find this from the Pythagorean. That doesn't quite look like Pythagorean. So maybe we should say result of Pythagorean theorem. Excellent. Okay, if we have 2 points, say we wanted to look at the distance between these two, all right, we can think of the triangle, the right triangle, and then we're just looking at that length there, and the Pythagorean theorem gives us that. All right, and then of course the distances, these distances, that one and that one are given by what we've previously defined there. So, so that all works out quite nicely. Excellent. All right, so again, returning, this is all stuff that we are pretty familiar with, so returning to more ideas that we already know. The slope of a line. The slope of a line that passes through these 2 points. So if we're given 2 points, P and Q, the line that passes through them has some slope, and that slope is given by M, the usual notation, and it's given by the change in height, so y minus v, divided by the change in horizontal position, so x minus u. It is important that we keep the correct order here, so that y minus v and x minus u. Okay, order is important there. All right, if we happen to have x is equal to u, of course division by 0 is bad, and so the slope is undefined. So it has no slope or is undefined, and it's a vertical line. And it's better to say undefined. No slope is a little bit ambiguous because some people might mean that there's no slope, it's not changing. But that's what no change in height looks like. That you might say is no slope. Of course, that could also be interpreted as a mistake, right? That has a slope and that slope is 0. But to say it has no slope, it seems a little ambiguous. So in order to be clear, we really should use the language of the slope is undefined or the slope is 0. Okay, so if we want to say that it's a horizontal line, we would say the slope is 0. And if we want to say that it's a vertical line, we would say that the slope is undefined. And that would be perfectly fine. And in fact, that would make things very clear. All right, so when we're finding the slope of a line through 2 points, right, we're choosing 2 points to find that slope. So does the slope change based on what 2 points we're considering on that specific line? Okay, so if we have a line and we choose 2 points, does it matter which 2 points we choose? Of course not, we already know that. But can we actually see this? Can we show this? Yes, we can. So if it did matter which points we used, then the definition of slope would actually be quite a useless definition. But again, it in fact does not matter what points we use, and we can show that. So let's consider this diagram here, right, to help us show that the choice of points does not matter when we are calculating slope. All right. So with these 4 points given, let's consider the 2 triangles made by considering the horizontal and vertical lines through these points. So we're going to, if we consider the vertical and horizontal, it's going to give us a few new points. So let's call this one T, where they intersect, and its coordinates are the x coordinate is given by u, and the y coordinate is given by y. And then here, let's call this point of intersection, we'll call it u, and the x value here is s, and the y value here is z. Excellent. So a couple things to notice here. Notice 2 things. First, the 2 triangles that we have created, triangle PQT and triangle RSU, are right triangles. Okay, excellent. Also, notice that the line through PT is parallel to the x-axis, and that is parallel to the line RU. And why does that matter? Well, by the converse of the corresponding angles corollary, we would have that angle QPT is congruent to angle SRU. Excellent. So what does that give us? Well, that tells us that this angle and that angle match, and that this angle and that angle match. Once we've identified that, then we can actually say that these 2 triangles are similar to one another. So by angle, the 2 triangles, triangle PQT and triangle RSU, are similar. Of course, I could have used appropriate notation to write that in a shorter manner. But that tells us that QT divided by SU is equal to PT divided by RU. Okay, so we have, right, we have our right, they're similar, so the ratios are equal to one another. And this word is escaping me. Hold on a minute, and I'll tell us what it is. Definitely hit the wrong button. So there's a nice long pause there where you're just looking at me instead of me pausing the recording. I'm sorry about that. That'll be okay. So I scrolled back to the notes for section 19 on similarity. And what I was looking for there was the sides are proportional. So we have a constant of proportionality. So we get that these ratios are equal to one another. And I'm going to pause this for 1 second for a group that's coming by. All right, that's just a few distractions there. Let's get back to where we were. So we observed by angle that these two triangles are similar to one another. Hence, we get that these proportions are the same. Okay, QT over SU is equal to PT over RU, okay? But if we multiply both sides by RU and SU, and then we go ahead and divide both sides, let's see. Actually, we just need to divide both sides by PT and multiply both sides by SU. That's all that we needed. So that is, we have QT divided by PT is equal to SU divided by RU. And what good does that do us? Well, that's QT divided by PT is equal to SU divided by RU. Rise over run is equal to rise over run. So if we use the coordinates of those points, right, if we use our definitions of distance for horizontal and vertical lines, we get that V minus Y divided by U minus X. Right? We've chosen wisely here so that way we don't have to worry about absolute value signs. But that is equal to T minus Z divided by S minus W. But in particular, these are the definitions for slope. So we have that the slope of the line passing through PQ is equal to the slope of the line passing through RS. And that's exactly what I wanted to say because that's the same line, okay? So notation there, slope of line passing through P and Q, that's this guy, and R and S, that's that guy. So slope of the line passing through P and Q, slope of the line passing through R and S. All right, so we've reintroduced ourselves to coordinate geometry, something that we're already familiar with. And we'll take a look at a few other concepts in just a moment. So I'll see you guys back here, continuing on in coordinate geometry.